All right, next we have Professor Ramos. He's a professor in robotics and machine learning at the School of Computer Science at the University of Sydney, and a principal research scientist at NVIDIA. He received a bachelor degree and master degrees in mechatronic engineering at the University of Sao Paulo, Brazil, and a PhD degree at the University of Sydney, Australia. His research focuses on statistical machine learning techniques for large-scale Bayesian inference and decision-making with application in robotics, mining, environmental monitoring, and healthcare. And between 2008 and 2011, he led the research team that designed the first autonomous open-pit iron mine in the world. He has over 150 peer-reviewed publications and received the Best Paper Awards and Student Best Paper Awards at several conferences, including RSS and the Australian Conference on Robotics and Automation, ACRA, and the European Conference on Machine Learning, ECML, and RSS. So please welcome Professor Ramos.
Thank you. Should I share my audio, or is it being captured elsewhere?
No, you can.
Okay.
You can turn it on.
Yeah.
Can you?
Yeah, I think it's on now.
No, it will go through the
Oh.
Yeah.
All right. Thanks for having me. Thanks for organizing this workshop. Such an important topic for me, for my research, and for everyone who has been working on this. I want to start this by talking about some of the complexities I see in motion planning. Right. We already watched some of the talks in motion planning, and we see here, even in this very simple 2D example here, where I'm doing parallelized optimization for the curves there. I have one starting point, one end point, and I'm trying to find the best path that connects these two according to some cost, right? So when you see what in the middle is some kind of obstacle, right? So I want to avoid those. As I carry on trying to continue to optimize that, I started to have these modes that start to collapse into areas of that path. So, all right, so the problem is actually very multimodal, even in 2D. So let's see what happens when we try to do that in 3D. And then you have this kind of explosion of paths, as you see here, right? There's a lot of potential paths. So it's actually a very multimodal problem, right? Even this GPU here is not very good and struggles even to render that in real time. So the problem is complicated. Let me make it, so that's the first dimension, right? So it's very multimodal, right? The problem of optimizing for paths is actually very multimodal. There's another thing, the problem is highly structured. So we're looking at paths, so there's a sequential nature to it, potentially very high dimensional. And when I'm comparing paths, I might have paths that equally well satisfy the goal, but they might have different lengths. Whatever you are representing that, I might represent a path with 5 numbers, and I would like to represent the path with 10 numbers, and I'd like to compare them, right? So there's that different dimensionality kind of issue as well. And then we might have real-time demand, so we want to be as fast as we can to this. So it's a very tricky problem. Is there any hope, right? So I want to go back a few years and start by looking to an area that has evolved a lot and actually allow us to rethink of algorithms for motion planning and other things, right? And starting in Theano, right? Theano 2007 was perhaps the first differentiable programming kind of library that you could just write your functions in Theano and you get the derivatives for free. Then we've seen TensorFlow, PyTorch, which I guess a lot of people use here, JAX in 19. Each one of those libraries optimized for parallelization as well, but also differentiability. So people don't need to worry about differentiating things by hand, to the point that PhD students don't learn to do differentiation anymore, from what I could see, right? But things are actually evolving beyond just differentiable programming languages. Other fields, like in statistics, started to build languages for probabilistic inference using differentiability, right? These are two examples, so Pyro and PyMC. So you can go beyond just dealing with cost functions that are differentiable to start thinking about inference as a differentiable problem. And also more recently, we start seeing this probabilistic languages for simulation, right? So we have here Taishi, created at MIT, and Warp from Miles McLean at NVIDIA, who essentially wrote a library that allow you to, if you write your physics problem in terms of Warp kernels, you get much faster, actually, performance than JAX or PyTorch. Okay, so there is some hope. The other thing is the evolution of hardware, right? So we went from NUCs, which we would put on the robot, to larger GPUs, to something like Jackson. So a Jackson today can do very much twice as what a Quattro used to do just a few years ago. So hardware is evolving, and little edge computers like Jacksons are playing a big role in that. So with these things in mind, I would like to design algorithms here to solve motion planning. They have these kind of three ingredients here. One is I want to leverage parallel computation, and we have watched quite a number of talks on how to do that efficiently. I would like to leverage differentiability for fast optimization, so I can actually do gradient descent type of methods as part of this. And I would like to have some notion of diversity among the solutions, such that modes don't necessarily collapse, but I actually have a spectrum of solutions, at least at the beginning of the optimization process. So instead of treating everything as independent, which is the invariantly parallelizable kind of solution, I would like to connect each of these optimizers such that I cover some spectrum of it. Okay, so let's start with this. And the first work I'm going to describe is called Kurobo. The main citation is there by Bala, who wrote Kurobo back in 2022. And the idea is to parallelize the entire process of motion planning. So that includes the planning itself, but includes collision checking, includes differentiability of the cost functions, and so on. And Kurobo can be extremely fast, as you see, right? So a few milliseconds, you do everything together. So let's see the elements of Kurobo, right? So revisiting our problems here. So usually you have this kind of two sectors, right? Two fields, right, inside motion planning. The graph plane type of style, where you most likely gonna, have some global properties in there, but that doesn't mean they are optimal. In many ways, you see the search is global, but sometimes you get motions that are not as desirable as you'd like. You might have parallel trajectory optimization in here, so it's faster to optimize, but also not the best. Kurobo tries to combine these two things to get something that starts with a graph search, optimize over the seeds, and then give you the solution to that, right? The way it works is separate the problems into a few steps. So the first step is parallel inverse kinematics, which you can run several instances in parallel. So you can see, a few thousands of this. So that's all implemented in a parallelizable manner with CUDA kernels. All right, I'll talk a little bit more about that. So we do inverse kinematics. After doing inverse kinematics, we can do the parallel trajectory optimization, where we leverage all the collision checks and everything. So it looks like something like this. So initially, there's collisions and all that kind of stuff. And as we go down through the optimization, the problem becomes better and better, and we are collision-free at the end. But obviously, some problems really require some search at the beginning. So Graph Planner help us a lot, right? So we can use Graph Planners, whatever Graph Planners you have, to seed this entire process, as long as it's implemented in a fast way. There you go. When we optimize that, we can even do solve problems like this where the arm was under the table. And you can add other costs to Kurobo to allow for shortest trajectory and so on. So you can actually tune that to the way you want while maximizing the success rate. All right, we tested Kurobo on a number of problems, and you see here, Bali is really good in generating these animations, right? I don't know how he does it, but you see all the reflections and so on. But the cool thing is it actually works really fast. And even better is that the entire package is open source, and each individual component, collision detection, parallel optimization, is implemented using CUDA kernel, warp, and NV blocks for the space representation there, right? So it's a library that is modular. You can take a look at it, and you're gonna have you can take whatever you want, right, and using your own algorithm. Now it does parallelization kind of naively, right? Every chain is independent of each other. You can apply some of these ideas to task and motion planning as well, and that's the work that we're going to show at RSS tomorrow, where we are doing task and motion planning. First step is we generate a plan skeleton with a bunch of possible plans. Each one is parameterized by continuous variables. And then after everything is in continuous space, we do full evaluation of that. There will be more details at the conference. But the cool thing is it's actually very fast to solve them. So here's one example. Place the objects into the Z camera box. So the first thing it does, it looks around to build the 3D model and use some PLM to do the segmentation. And you see how fast the planning was, right? To reason about the grasping position and the place positions for these things. And then the problem can be very easily modified. We can back again, change heights, add blocks, put a jetson in there, and now put all the blocks on the jetson. And you see planning, maybe took 5 seconds, 6 seconds, and so on, and then start the execution. Again, that's by leveraging the parallelization together with differentiability. All right, so these two works really leverage parallelization and differentiability, but there is one extra component to it, which is where I want to actually dedicate more of time to this, right? Which is diversity, the notion of diversity when we are doing parallel optimization. And everything started when I look at the problem of parallel optimization in the lenses of computing some kind of non-parametric distribution, right? If you think about what you're doing when you are parallelizing things, and you think at each chain as an independent kind of sample from a distribution, you can borrow a lot of techniques from a probabilistic inference to actually reason about the entire set of solutions, not just one, but the set, right? I started my research as someone doing probabilistic inference before I was doing any robotics. So we like to show graphs like this, right? Still, evolving, but it has been always our goal. We want something that is fast, so it's at the top, algorithms that are fast, but also heavily automated. And if you look at things like MCMC, which is what people in stats would use, it's highly automated, but it's not fast at all, right? Particularly the standard sampling methods in the past. What we see happening more recently is that with parallelization and with differentiability, we can try to push the boundaries of probabilistic inference methods more and more towards the top right. And the technique I'm going to show to you today kind of heads towards that direction, right? And we're going to see how to make it even better. So just briefly mention what happened in the stats community since 2-3 decades ago. We used to have MCMC, Markov, Monte Carlo. There's a lot of theory. We know it works. It's correct, but very slow, Well, then the optimization folks start looking at the problem from the optimization lenses. Instead of computing samples from a distribution, let's actually try to find an optimization problem that matches distributions. One is the distribution you are trying to approximate with some kind of parameterized way. That is what is called probabilistic variational inference, which is fast, but could be inaccurate because you're making assumptions over the type of distribution you are covering. And some people even use these things called argmax, right? If you're just interested in one point of that distribution, you can be fast and do optimization, but no uncertainty quantification. One of my favorite methods until 2011 or 12 was this algorithm called stochastic gradient Langevin dynamics, which is part of the MCMC set of tools, right? So we're trying to reconstruct the posterior, as you see here, and there is a chain going around, bouncing and collecting samples from that posterior. And every time I collect a sample, I add it there to create this this version. It's an excellent algorithm, leverages differentiability, but it's just one chain. It's very difficult to parallelize. I'd like something a little bit better, which is why we started looking to this thing called Stein variational gradient descent. Evangelist already mentioned this, but it's actually the entire Stein theory in stats started quite a while ago, just to prove theorems. It wasn't until 2016 that we actually saw an algorithm that leverages all the theory to come up with something useful for us. And here's the idea, right? It can represent general distributions as a non-parametric collection of points. You see a 2D problem here. It exploits differentiability, as we shall see. And all the particles, as opposed to MCMC, where you sample each one sequentially, all the particles are initially sampled. So you have a pool of particles, and then you propagate that according to some kind of law. So if these are the distribution I'm trying to capture with these three modes with some points, this is the dynamics of Stein. Okay, so how the dot points representing the distribution flow into this spectrum, right? You can see this actually as a generalization of diffusion methods. So, diffusion are so popular these days, right? Where instead of having, this a learnable function that go from one step to the next, the functions here are built out of the cost function, right? But we're still doing some kind of flow, evolving from one distribution to another distribution. And that is done through this equation. It's actually a pretty simple equation to implement, right? Because suppose that you have a cost, and that cost somewhat, represented as a probability distribution here. I take the gradient of that, right? And X here is all my particles represented in the distribution, right? So I'm doing that in a whole batch of things. And I multiply that by a kernel. So I take each of these particles and I lift that into a Hilbert space and do a kernel over it. And this kind of follows the gradient of what you want to achieve. This other component is what is called a repulsive force that actually stops particles from colliding into each other, so you actually have better coverage, right? Well, this is actually a very interesting algorithm for us because it not just leverages parallelism and differentiability, but actually connects the chains in the optimization process. They are all part of the same big problem as a flow into that space. And you can add second order variations to it easily. So this is what happens when you add second order. You see that, at the very beginning, the second order component precondition the first one, and you have this stripe fits there and then continues to optimize. Or you can add constraints to it as well, where first the particles go inside the constraint area given by the green box here, and then find its way to capture the posterior. All right, but if each particle is a point on a distribution, they could also represent a full trajectory, right? It's just a higher dimensional point. Okay, so for example, these are parameters of a particular trajectory. And in a sense, Stein is doing a KL diversion. So it's doing variation inference between what you want and the set of particles that you are considering. And you can go back into this optimization process every time computing a new estimator, particle estimator for what you have. That's quite interesting because, well, if you know your cost, you can represent that as probabilistic inference in this way, right? Just following Bayes' rule, assuming that the cost is C, and theta are the parameters of my controller, for example. With that, you can derive what is called Stein MPC. So it's an MPC controller that is using kind of Stein optimization to it. You see the standard kind of MPPI on the left, and how Stein MPC was able to find its way through this little maze in there. And you see problems also when we have obstacles in MPPI, as you see here. You see the structure of the solutions, very Gaussian looking, and inside this particular modes. We can do much better when we have Stein, where the spread of the particles is much wider. So we're actually looking at modes from there until we find the solution, right? So it has better coverage in the area. And if you have that, you could do one extra thing, which is, well, you do Stein, and then you can eventually cut the repulsive force. You see all the solutions that Stein found. You can cut the repulsive force, then the trajectory start to collide as you would expect into the modes as you see that. All right, but there is one component I didn't talk to you about, and it'll take me maybe 2 minutes.
Yeah, I think we have like 4 or 5 minutes.
4 or 5 minutes, okay, perfect. Where I would like to, I've seen this term diversity everywhere in robotics, right? People all call, oh, I have a diverse data set and so on. And okay, but what do you mean by diversity? So I thought about trying to define at least one definition of diversity that I could apply in my Stein algorithm and see how well it would do. And when I started looking into that, the first question is, how do I compute distances between trajectories? Trajectories might have, or paths might have different lengths, right? I have trajectories that are short, long. My solution might be better with a short as opposed to a long one. And I would like to reason about all of this space of trajectories. So it turns out that there are some ways in the literature of computing distances between trajectories. These are some of them, right? For shed distance, for example, dynamic time warping. And they all have some drawbacks, right? Particularly computational time is not particularly good. They also don't take into account the full geometry of that trajectory. That's when I started looking to an area of mathematics that actually studies paths. And very recently, this new transform called path signature became kind of popular in mathematics, right? And the idea is the following, right? See if you can get the concept here. Let's say I have 2 functions here. They're a function of time, and I'm plotting them as a function of time. One is x, the other y, all right? That's the plot there. And then I take the time and I just square the time in there. So you see the 2 plots on the left look very different than the time I have here, just by squaring the time component, right? Now, what is more interesting, the mathematicians were looking to that, is that, well, if I plot x as a function of y, not as a function of t, but as a function of y, they actually are the same. Doesn't matter the parameterization I use for that path, if it's t or t squared. These are the same kind of path that is represented, no matter the velocity. It's about the geometry of this, the shape of it. Well, with this, they design an entire theory to actually represent paths, right? Represent the structure of paths that we would like to leverage. Here it's called the signature transform, the path signature transform. Is the idea that you can build representations, just like you're doing Fourier transform, but this is particular for paths, where you can look at the space of paths and create representations that don't lose any information, right? The information is all embedded in there. It's invariant to parameterization, so I can change, time. I can add translation invariant, and I can compute that very efficiently. That is done by iterative path integrals over the entire space. But what you ended up having is, some basis functions, right? And why they are cool? There is a theorem that says that if I take a path and represent as a path signature, any nonlinear function of it can be computed as a linear function of the path signatures. So it gives you a projection into a Hilbert space, but in a linear way. So you can use that to represent costs much more effectively. We can replace path data with the signature data. So forget about the path itself, the original, dots. You're only looking at the signatures. And it doesn't depend on dimensionality, right? So let me just speed up here. With that, we define what is called a kernel of signatures. And this kernel of signatures now leverages the shape of the structure of the paths in there. And it turns out that there is another very interesting paper in math where they show that this kernel here can be solved by solving a PDE or using a numerical method from the PDE, which scales very well on a GPU. So it's fully parallelizable, right? So you see here the dependence on the dimensionality. It's kind of constant. It only depends on the number of steps, the length of that path. All right. So now we have a definition of diversity, which I can then apply to my Stein, motion planning. You see the differences in path styles that you see in there. This is all described in this paper. If you want to take a closer look, also code is available. And you can really see differences in when SGD versus Stein, and I mean, it's kind of difficult to see all the complexity of this path, but more interesting is that we actually have much better results than using Stein on motion planning problems like this, right? I've never seen a result that, they beat just putting the Stein kernel in there beats all the other motion planners, optimization-based motion planners, sometimes by quite a lot. All right, just to quickly summarize, motion planning is difficult with many solutions and local minimum. Differential programming, parallel computation give us some hope. And we saw quite a few interesting works here about that. Probabilistic methods, in particular, variational methods, time variational methods, have a potential for a lot of potential in motion planning. And if you have a differentiable cost and you have parallel compute through a GPU, you can convert that into probabilistic inference, and path signatures give you a definition of diversity that you can use to reason more globally about these things. All right. And these are some of the references from, and these are the main authors for the papers I mentioned. Yeah, thanks very much.